Hello! In this video we are going to apply partial fractions. It's a very important method. Let's see the objective. We are going to apply partial fractions in a very easy example. Okay, if we are going to understand this process, we need to start slowly. So this is the first example we are going to see about partial fractions. It's not difficult. I will try to explain myself as best as possible. And okay, let's see if we can just apply this method and understand all the process perfectly. What are we going to need? We are going to need a basic knowledge of algebra, calculus a little bit, and we are going to work with fractions, so keep this in mind. You should at least know how to manage them, how to deal with them. Okay, let's see. The example is simple. As you can see, this is a very trivial integral. It's indeed a very trivial integral. So I'm going to ask you something. I'm not going to give you the answer right now. You can just give me the answer if you want using the email if possible. Okay. This integral has no problem. You can just solve it like this. You only need to tell me, oh, that's perfect. I know it. It's blah blah blah. I'm not going to give you the answer, of course. But this integral don't need any method to be solved. If you remember more or less what was the list of integrals you need to remember, no problem. Okay, and by the way, you can use any method you want. Okay, I'm going to offer you a method, but if you know the solution, please use it. Don't expect that don't think that I'm expecting that you calculate step by step everything. My point is, I hope you are good integrating. If you are really good and you know the solution, give it to me. Okay? So, anyway, let's see a different way. I see a quotient. On top, a polynomial. On the denominator, another polynomial. The degree of the polynomial in the denominator is greater. So, perfect. What can we do? One option is partial fractions. Partial fraction is a process in which we take this fraction and split it in different parts, simpler parts, shorter parts, something that I can integrate directly without no effort. And how do we do that? What is the process? Okay, the process is correct, we can apply always, but be careful because when we offer you these examples, everything is prepared. Everything is set up from the beginning. So I put just x squared minus 1. It's nothing difficult inside. I can do it in a more complicated way. Yes, for sure. Okay? So let's start with this easy example. And if you understand the technique, you can apply it even if the numbers are not so nice and if the exercise is not so nice. Okay? So let's see. In this case, what we are going to do is to take the denominator, always, and factor the denominator, or write the denominator as factors. In this case, the only thing you need to do is to take the denominator, equal the denominator to 0, and solve it. X squared minus 1 has two solutions, 1 and negative 1. So, x squared minus 1 can be written as x minus 1, x plus 1. You don't trust me? Fine, perfect. Calculate the values by your own, and also you can double check that the product of these two polynomials is exactly x squared minus 1. Okay, so perfect. So we got x squared minus 1, it's written as x minus 1, x plus 1. Perfect. What we want to do is to take the fraction, the original quotient, and write it as a constant over x minus 1, one of the factors, and plus b over the other factor, x plus 1. Okay, that is the idea. Why do we want to do that? Because we know perfectly, I hope so, we know perfectly how to integrate a constant over x minus 1. And we know perfectly how to integrate 1, for example, over x plus 1. A and b are constants, and they are not going to make the integrals more complicated. It's just a constant. You just write it apart and integrate. So, my question is now, do you remember what is going to be the integral, for example, of 1 over x minus 1? If you have tell me, oh, that's very easy, it's logarithm of the absolute value of x minus 1, perfect. If you just give me the answer, oh, that's perfect, it's logarithm of x minus 1, Perfect, but be careful, okay? Normally the integral is the absolute value, a logarithm of the absolute value, because logarithm is a function that is not defined for the negative values. But okay, if you write a logarithm of x minus 1 without the absolute value, I will think that you are aware that the logarithm cannot be calculated for negative values, and then there is that the solution is only defined for the values that make this happen, okay? Let's see, let's continue. So the idea is to calculate a and b. Which are the values for a and b that verifies this equality, okay? How do we do that? The idea is we are going to multiply by the common denominator x minus 1, x plus 1. Both parts, okay? So x minus 1, x plus 1, it's exactly x squared minus 1. So if I multiply 1 by x squared minus 1, then this becomes 1. If I multiply a by x minus 1, x plus 1, x minus 1 can be simplified and the only thing left is x plus 1. If I multiply b by x minus 1, x plus 1, then x plus 1 disappears because it can be simplified with the denominator, and the only thing remaining is b times x minus 1. Okay, you don't do this normally in this way. What you do normally is just to, or when we get used to this process, we normally say that I'm making the two numerators equal. On this part, the numerator is 1. On the other part, if you just add these fractions together, again, you just factor these two quotients together. The idea is to multiply a by the denominator of b and b by the denominator of x minus 1. Cross product, okay, like this one. So the idea is at the end, what you have is 1 equals a times x plus 1 plus b times x minus 1. Perfect. Now, we need to solve for this. Which are the values for a and b that verify this equality for any value of x? It doesn't matter what is the value of x, this should be true. That is important, okay? Because you can think, oh no, this could be different for any values of x. No, I need this to be to be true for any value of x. What can we do? Okay, option 1. We just multiply a by x, a by 1, b times x, b times minus 1. We put everything with x together, everything that has no x together, and at the end, what we are going to have is a system of equations, okay? Because we are comparing two polynomials. That's too long, in my opinion. What can we do? If this is going to be true for any value of x, you can choose the value of x. Give me any value of x that in order to apply it here and solve it. Okay, I guess all of you are thinking in very easy numbers. I guess 99% of you are thinking, okay, if you take 1 or minus 1, this is going to be simplified very fast. Yeah, you can take any number, even a square root of 2 if you are a little bit brave, or any other number. I like pi and I'm going to put it in the equation. Okay, up to you. It's up to you. At the end, you are going to find the proper value. But let's take the easiest values. So, which are these values? Let me show you. Yeah, x equals 1. If I replace x by 1, this part disappears. That is a smart move. So, if this disappears, the only thing left is 2a equals 1. So, a equals 1/2. If I take x equals to minus 1, this part disappears. The only thing left is minus 2 times b equals 1. So, b equals minus 1/2. Oh, in just two movements, we have a and b. So it's a very smart process, and you already have the problem solved. Then I wanted to write this quotient as a sum of two fractions. Perfect, partial fractions process. So I just, that was a, but a is now 1/2. That was b is minus 1/2. That is the reason I just wrote the negative in between. And then the only thing left is integrate these two fractions. But this shouldn't be difficult, guys, okay? The integral of the first one, again, 1/2, we have been dealing with how to find this a and b, but now that we have it, I just wanted to put it apart, okay? So 1/2, it's move outside. 1 over x minus 1, the derivative of the denominator is on the numerator, perfect, is a logarithm of the absolute value of x minus 1. Minus 1/2, I just do the process again, this is a constant, move it outside of the integral, and then the integral of 1 over x plus 1, since the derivative of the denominator is on the numerator, it's a logarithm again. So logarithm of x plus 1. In the last part, I just apply a property of logarithms. The logarithm of something minus the logarithm of something is the logarithm of the quotient. So it's more beautiful to write the last equation like this, okay? So guys, we have applied this method, partial fractions, in order to solve an example. The idea is that we need to review this process. It's not difficult, I promise you. Maybe it takes time, but as you can see, in no time we have been dealing with an example. Could be more difficult? Yes, of course. Could be much more difficult? Yes, of course. Okay, but we will see this in future videos. Thank you for your attention, guys.